You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our Worth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronics What's Up podcast. The growing trend to miniaturize wireless communication devices has led to decreased PCB sizes and increased component densities. Although this shift to miniaturized technology has aided many areas of electronic design, it constrains RF front-end design. Due to the nature of antennas sending and receiving electromagnetic signals, they interact and are affected by the entire surrounding environment and are extremely sensitive to electromagnetic fields. This can be extremely problematic for RF engineers when integrating into a design and antenna that is small but also has good gain and efficiency in the frequency range of operation and is able to work in different PCB environments. Multi-layer chip antennas are an interesting choice for those engineers who are restricted by cost and space requirements in wireless system design. Low-temperature co-fired ceramic, or LTCC, multi-layer chip antennas are formed from several layers of dielectric material that are pressed and fired together into a monolithic structure. Each dielectric layer has patterned metallization on the surface that connects to other layers through vias. The layers and vias form a helical multi-layer antenna. In today's podcast, we'll explain how to get the maximum performance from the Worth Electronic MCA multi-layer chip antenna with respect to antenna placement on a PCB and effective impedance matching. We'll begin by discussing the antenna design and simulation. The importance of antenna placement is clearly understandable when you consider the structure and the operating principle of an antenna. For this purpose, the MCA multi-layer chip antenna has been simulated in a 3D electromagnetic design tool to illustrate electromagnetic fields and radiation patterns. The multi-layer chip antenna consists of metallic layers connected by vias and enclosed by ceramic material. The inner conductors and vias form the radiating multi-layer meander structure. Electromagnetic fields are generated by the currents on the inner conductor. This self-resonating meander structure allows the component to be smaller than a monopole antenna while achieving comparable performance. The antenna is designed to operate at a center frequency of 2.45 gigahertz with a 10 decibel bandwidth of more than 250 megahertz with more than 30 decibel return loss, as evidenced by the simulated S parameters. Next, we'll talk about antenna PCB placement considerations, including corner placement, side placement, and sometimes even ground placement. When incorporating an antenna into an electrical product, some of the most critical stages of product development are the design of the PCB layout and the device enclosures. This is due to PCB component density continuously being increased to reduce the size of the device while not impairing the function of the design. Now, antennas can be extremely sensitive to power and ground planes when functioning as a quarter-wave monopole antenna system. However, if the feed line and ground plane dimensions are carefully and intelligently taken into consideration when designing a chip antenna PCB, performance comparable to a half-wavelength dipole antenna can be achieved. The positioning of the MCA is critical to achieving optimum antenna gain and performance. The antenna gain can be significantly reduced when the design rules are not followed. Generally, the closer a grounded conductive material is placed to the antenna, the lower the performance will be. Placing the antenna on the PCB corner is generally the most desirable location. This typically results in better antenna gain. If the antenna is placed in a corner, It'll be surrounded by a ground plane on only two sides. When the antenna is placed in the corner of a PCB, the following criteria should be implemented to achieve optimum antenna performance, and you can see this performance in Figure 1 attached in this podcast. The antenna can also be placed on the side of the PCB, where it will be surrounded on three sides by ground plane when it's not possible to place the antenna on the corner. But in this case, antenna performance might be reduced. Figure 2 shows design rules that should be followed to ensure the best performance in this position. And lastly, and in extreme cases, the antenna may be placed over or between ground planes. However, it must be remembered that having any metal plate or battery above or below the antenna will also result in significant degradation of antenna performance. In some cases, there's no other alternative except to utilize the area above or below the antenna, so careful considerations must be taken during the design and prototype stages to ensure sufficient antenna gain performance. In this case, the ground planes must be a minimum of 6 millimeters above or below the antenna area. Special considerations need to be taken when an antenna is placed in an enclosure. Completely encasing the antenna in a metallic casing, housing, or an enclosure is out of the question, since the majority of the power from the antenna will be reflected back into the device. Housing made of non-conductive materials such as plastic and glass are much easier to incorporate into a design than conductive materials. Although the power is not reflected, the impedance and overall performance of the antenna will be affected. Depending on the non-conductive material, permittivity, and proximity to the antenna, a significant frequency shift of up to hundreds of megahertz can be expected. This needs correcting with appropriate impedance matching. Usually when a chip antenna is designed, the electrical specifications are measured on a manufacturer's test board and in free space. In reality, an antenna will be operated in an environment that results in an impedance transformation, regardless of whether it is intended or not, with the impedance mismatch being different for every device. Antenna return loss is a good measure of how well an antenna is matched to its feed line. Return loss quantifies the amount of power being reflected by the antenna mismatch back to the source. Of course, in an ideal world, a perfectly matched antenna would transmit 100% of the incident power with 0% return loss. But since no components are ideal, there are always undesired losses. A return loss of 10 decibels is acceptable and means 90% power transfer, while a return loss of 20 decibels is equivalent to 99% power transfer. Impedance matching is carried out to mitigate mismatches caused by board placement, the surrounding components, and enclosure, and the presence or absence of overlapping ground planes. This requires the addition of capacitance or inductance to an antenna circuit to ensure the voltage and current are in phase. This minimizes the amount of reflected power and reduces voltage standing wave ratio, or VSWR, meaning efficient power transfer to and from the antenna. Therefore, the maximum power is being transferred to and from the antenna by the feed line. In the design and development of a product, special space needs to be allocated for a matching network during PCB design for RF inductors and/or capacitors. The values need to be determined and optimized during the prototyping stage. Matching networks are implemented as close to the load or source as possible, as the length of feed line will have an effect on the impedance matching and power transfer. At microwave frequencies, the input impedance changes with respect to distance from source, unless the transmission line is matched to the source or load with the characteristic impedance. The impedance can be measured with the help of vector network analyzers, or VNAs. VNAs are able to measure the amplitude and phase angle of a system. The measurements can be displayed in a number of formats, but S parameters and the Smith chart are the most useful tools when matching the impedance of an antenna. S parameters are part of a larger group of similar parameters and use matched loads to characterize a system. For S parameters, the system containing any number and variety of components is treated as a black box with ports. S11 provides information about the amount of power that is being reflected, or turn loss, back to the port, while S2 is the power that is being transmitted. It's the insertion loss from port 1 to port 2. Measurements are represented as a complex number that corresponds to magnitude and phase angle. This can be displayed in either Cartesian form, where magnitude and phase are presented in decibels and degrees, or in polar form, where a data point represents a measurement at one frequency or a locus for a data spectrum. The Smith chart is a graphical tool that plots the complex impedances in polar form, and it's commonly used by RF engineers to facilitate transmission line theory problems. The true power of the Smith chart lies in its ability to display multiple parameters of interest simultaneously. Some of these parameters include impedance, admittance, S parameters, VSWR, and constant gain circles. In our attached figure 3, you can see the collection of circles, arcs, and lines. Now, while this can initially seem quite intimidating, in reality, only a few things need to be understood to correctly interpret it. The red circles and arcs towards the right are resistance and reactance lines respectively, and they are always touching the chart outline at 90 degrees. It needs to be remembered that the resistance and reactance remain constant if the movement is along these circles and arcs. On the left side, the blue circles and curves that are touching the outline of the Smith chart at 270 degrees are called conductance and susceptance lines. At the center of the Smith chart is the 50 ohm point, which is also the point of interest since the characteristic impedance of antennas is almost always 50 ohms. This Smith chart also includes a green VSWR circle in the center. Once a measurement is made, it appears on the Smith chart as a complex impedance with resistive and reactive components. The goal in this case is to move the impedance at the antenna operating frequency to the center of the Smith chart at 50 ohms. This can be achieved using RF inductors and/or capacitors. A pi network is especially useful for this purpose as it can always be used in a flexible way for antenna tuning to 50 ohms from almost any other value. In typical scenarios, only two reactive components, the inductor and capacitor, are needed to match the impedance to 50 ohms, but a pi network should always be implemented in PCB design to offer maximum flexibility later in the development process. A series capacitor will move the impedance in a counterclockwise direction along the resistance circle. A series inductor will move the impedance in a clockwise direction along the resistance circle. A shunt capacitor will move the impedance in a clockwise direction along the conductance circle. A shunt inductor will move the impedance in a counterclockwise direction along the conductance circle. Using those principles, it can be visualized what components need to be used and in what topology to achieve the desired matching. So now that we know the design rules needed to achieve the best performance characteristics from the MCA, we can demonstrate an example of the matching process. This was done on a demonstration board with the RF inductors coming from the MK Multilayer Ceramic Surface Mount Inductor Design Kit. This is available to customers with free refills, and Keysight's E5071C Vector Network Analyzer. Before calibration, we set the VNA to a frequency range that covers the entire band of interest and a little more. So for example, MCA covers a frequency range of 2.4 to 2.5 gigahertz, so the VNA was set to 2 to 3 gigahertz. It's important to correctly calibrate the VNA according to the manufacturer's specifications to negate the phase shift caused by the connecting cable. Without correct calibration, achieving a matched antenna could still be possible, but it'll be much harder to interpret the Smith chart data. To check the quality of the calibration, a short, open, and load can be connected to the cable and the measurements viewed on the Smith chart. If the calibration is correct, the trace should appear on the left, which is short, the right, which is open, and center, which is the load of the Smith chart. Next, set the markers at the lower and upper range of the antenna. For lower frequency antennas, it is possible to use a 0 ohm resistor to short the pi network to see how the antenna is performing without a matching network. But at higher frequencies, the parasitic inductance of a 0 ohm resistor becomes significant enough to affect the network. Therefore, a capacitor with its self-resonant frequency at the antenna frequency can be used as a short. In theory, when the capacitor is used at its SRF, the impedance should be resistive and not reactive. Although the capacitor has ohmic impedance, at these frequencies it will work as a short with no reactive element, which is better than a resistor with parasitic reactance. This gives important information about the impedance of the antenna in situ and indicates what capacitance and inductance needs to be added to the matching circuit to bring the markers to the center of the Smith chart and achieve a matched impedance. Software and online tools can also be used to select the component values. From our Smith chart shown in Figure 4, we can see that 4.8 nanohenry of parallel inductance and 1.6 picofarad of series capacitance needs to be added to bring the voltage and current into phase for maximum antenna efficiency. Since standard RF inductors and capacitors are available in a limited number of values, a 4.7 microhenry inductor and a 1.5 picofarad capacitor were used and the S parameters remeasured. We can see that although the WE-MCA is performing better than unmatched antenna, the gain and impedance matching is still suboptimal. Now, this is where knowledge, practice, and experience will really pay off in optimizing the matching circuit. It'll normally take a number of repetitive steps to achieve optimal matching. For our example, the 4.7 microhenry inductor was replaced with a 3.9 microhenry inductor and the antenna was remeasured. The result with a 3.9 microhenry inductor and a 1.5 picofarad capacitor shows that although the impedance is almost matched, the return loss is not below 25 decibels. This is more than sufficient for the majority of applications where a wide bandwidth is needed, but it could still be improved. In the final step, the inductance of the matching network was lowered by replacing the 3.9 microhenry inductor with a 3.3 microhenry inductor. With a 3.3 microhenry inductor and a 1.5 picofarad capacitor, optimal impedance matching is achieved with the data point of the resonant frequency very close to the center of the Smith chart, a return loss of around 30 decibels, while maintaining a 10 decibel bandwidth of 500 megahenry. In our final attached Figure 5, we can see the importance of bringing together theory and an iterative process to accomplish optimal antenna performance. It is understood that the matching process may need to be repeated at numerous stages of the design process for system verification. In summary, the WE-MCA multi-layer chip antenna can be used for a variety of wireless data applications, including Bluetooth, GSM, Zigbee, and WLAN. It has a low profile and weight while having high gain and temperature stability. The chip antennas can be easily implemented without specialist knowledge or RF expertise while maintaining performance. The matching of WE-MCA multi-layer chip antennas can be a simple process when the fundamentals of impedance measurement and matching are understood and a logical, repetitious process is followed. For more information and to sample the WE-MCA multi-layer chip antenna, visit Worth Electronic online. You can also download this application note by clicking the link available in this podcast. You are listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our Worth Electronic technology specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronics What's Up podcast.